Good afternoon, everyone, and good afternoon to the respected professors, scientists, and students. Myself, Dr. Himashri PR, Junior Scientist at NATPAC. It's my pleasure to welcome you all to the TransPedia Research Talk Series organized by KSCST National Transportation Planning and Research Center NATPAC, through which we aim to provide a platform for the researchers in the field of transportation engineering to share their knowledge and expertise with us. These talks will give us insights into emerging trends and cutting-edge technologies in this. I would like to express my all of joining. We have a researcher lined up who will be sharing valuable insights with us on the topic saturation flow estimation at signalized intersections with multi-class traffic. Before we begin, I would like to invite Dr. V Mathew, Director NATPAC, to deliver the welcome address.
Good afternoon to all. The National Transportation Planning and Research Center is an institution of Kerala State Council for Science, Technology and Environment. And this NATPAC was established in the year 1976, which is coming under the Science and Technology Department of Government of Kerala. As all of you know, we work on multi-modal systems of transportation covering road, rail, water, and air. And we have creatively contributed to the development of transportation country, both as concern as well as an advisory role also. NATPAC currently we have as on today we have 25 scientists, 8 technical officers and 7 technical assistants, and they are working under 5 divisions, namely Transportation Planning and Engineering Division, Traffic Engineering and Safety Division, Highways and Bridges Division, Water Transport Division and GAS, Information, License and Training Division. Our research activities are guided and monitored by the Research Council under the chairmanship of Professor V Mathew and Professor Lalita from IIT Madras, Professor Reddy from IIT Kharagpur, Professor Anjaneyulu from NIT Calicut, Dr. Velmurugan from CRRI, Professor Asalada from College of Engineering, Trivandrum, are the other Research Council members. We have been organizing a series of monthly online lectures. It was TransTech Talk Series, which was started in the month of February 2023. It was attended by students, faculty, researchers, and stakeholders. Already 7 such talk series are over. Again, by Dr. Srinivas S. Fulgutra, Dr. Rajiv B. Malik, Professor Jayakrishan R., Engineer Tony Mathew, Dr. Varun Varghese, and Dr. Sunanda Disadayage, and Dr. Neeraj Butch. And again, in the Research Council, we have discussed that we thought we will invite the just completed Ph.D. scholars or the PDF scholars to share their research experience with the scientists as well as students working across India or internationally. And our team named this talk series as TransPedia Research Talk Series, again motored by the Research Council. And today we have the first talk, and in which Professor Dr. Tom is also attending, is the RC chairman and professor at IIT Bombay. Today we have with us Dr. Remya K Padinjarapat, who happened to be my student as well as Professor Tom's students. She graduated from NIT Trichy in the year 2013, and afterwards she has completed her Ph.D. from IIT Bombay under the guidance of Professor Tom. I welcome both Professor Tom as well as Professor Remya for this first talk. Of course, at a very short notice, I invited Professor Tom to attend and inaugurate this talk series. He agreed for that one. Thank you so much for that one, Professor. I welcome you. I welcome Dr. Remya. I welcome my scientist, then other students from different institutions, faculty, and all. Welcome all of you. And we wanted to have this talk series in the beginning, basically one talk at least in a month. And if more demand is there, we thought lesson we can have 2 talks per month. So today we have the first talk. Welcome all of you once again to this talk series.
Thank you, sir. To officially inaugurate this session, I would like to invite Dr. Tom V Mathew, Professor, IIT Bombay. Please, sir.
Good afternoon, and really glad on many counts this noon time. First, we have been looking at many of the planned projects at NATPAC, and one observation that I made earlier was I've hardly seen any projects or studies in the area of traffic signal design and so on, etc. And on this count, I found this topic is really paving the way for hopefully some studies in the area of signal. And designing traffic signal is one area that we require a very in-depth understanding of traffic dynamics. And this talk, I think, is really a welcome step in that direction. And second, also congratulate NATPAC on taking research seriously, and also to interact with various scientists who are already established, and as well as new scientists who are done very in-depth studies on various topics is really a welcome. And that will really challenge the scientists and other staff of NATPAC and other students who are attending, which will help to expand our grasp on various subjects, not only the area that we work, but also the allied areas. So that way it is very good. And then and especially today, I'm glad that Remya, who worked with us, is also presenting, and I'm really thankful and glad that she is there, and also share her experience. And so that way, I'm glad. So with this, I encourage all the scientists and make use of this talk, not only this talk, but also all the series of talk that is coming there. And so with this, I would like to formally inaugurate this talk and welcome Remya and to deliver the talk.
Thank you, sir. Now I would like to invite Shri Tinku Casper De Silva, Junior Scientist NATPAC, to introduce the speaker for today's session.
Dr. Remya K Padinjarapat is presently working as a research fellow at National University of Singapore. She graduated in civil engineering from University of Calicut and obtained MTech in transportation engineering and management from NIT Trichy. She completed her doctoral degree in transportation systems engineering from IIT Bombay in 2021. Her doctoral research was on the topic estimation of passenger car units at signalized intersections and mid-block sections of urban roads having multi-class traffic streams, under the supervision of Professor Tom V Mathew, Department of Civil Engineering, IIT Bombay. Her areas of research interest include traffic flow theory, driver behavior modeling, traffic and driving simulation, and transportation systems design. Today, she will be delivering a talk on the topic saturation flow estimation at signalized intersections with multi-class traffic streams. On behalf of NATPAC family, we welcome you to the session.
Thank you. Madam, I would like to welcome you to deliver the talk.
Hello, good afternoon, everyone. Yes, so I will get started with the talk. Let me share the screen. Please let me know if you can see it.
Yeah.
Is it visible? Yes.
Yes.
Okay.
Yes.
So yes, thank you for the introduction. And it's a privilege to be the first speaker on such a talk series. So you can see here, I'll be talking on the saturation flow estimation at signalized intersection and with multi-class traffic streams, which is generally seen in India. I'm presently a research fellow at NUS, but the work that I'm presenting will be based on my PhD, which I did at IIT Bombay with Prof. Mathew. And the work is also a part of the project, the development of Indian Highway Capacity Manual, which obviously led to the book, The Indo HCM, which most of you might have seen. So I was a part of the team working with the chapter on signalized intersection. And yeah, so the work is basically a part of the greater project. So I'll start with the basics here. The first is what we have intersections, and they are obviously an inevitable part of a road network. So there are various types of intersections: uncontrolled intersection, there are channelized intersections, rotaries, uh, signalized intersection, and grade separated. Among them, signalized intersection is most popular in cities and in where there is a lot of city traffic and pedestrian traffic involved, because it works on the principle of time sharing, where different participants or different moments of traffic, they share the same space at different sections of time. So it's a very highly efficient system for city traffic. So considering the traffic types, basically, you all will be very much aware, there are homogeneous as well as there are multi-class. Homogeneous is obviously vehicles have a similar types of vehicles, or the behavior of vehicles will be quite similar. They'll be lane following. But in multi-class traffic streams, there will be a lot more varieties of vehicles, because of which the behavior of vehicles is different, which results in a weak lane discipline. And specifically, these characteristics becomes very strong, specifically during queuing and queue discharge conditions, which is of very much of importance when we are designing signalized intersections. So again, coming to the basics, if in an ideal condition, vehicles will align themselves in a very orderly manner, and during the green time, the discharge is seen such that there is a lag. Excuse me, I'll just change my point. Yes, so there will be a lag in the initial discharge, and once a point is reached where the vehicles will have a steady flow, and this is the maximum flow that is seen at the intersection, and it is called the saturation flow, which is of importance for us at this moment. So why do we need to measure saturation flow? It is the maximum flow in a cycle, which eventually translates to finding out the maximum flow that an approach can take in, and it is used again to find out the capacity of an intersection, which is the maximum flow among all the approaches, and again redistributed to find out the signal timings, which is proportionately divided based on the capacity of each approach. But when it comes to multi-class traffic streams, what happens is, this is a very vague representation of how queuing would generally take place in a multi-class stream, because the vehicles will tend to take up whatever gap is available and try to move ahead in the queue. So we observe a diamond-shaped queuing pattern here, and the vehicles, they tend to creep forward, which is known as headway compression. They just even though the queue might be standing, the vehicles might slowly move ahead, which is a phenomenon called as headway compression. And then of course there is the infiltration by smaller vehicles towards the front of the queue. And the smaller vehicles, they just clog around in the front of the queue, and the, when we see what we see during discharge is that there is no particular first in first out pattern. For example, you can see the two-wheelers here, they come from the extreme end, and they come and take their turns. They do not they, although they might not be the first vehicle in queue, they tend to leave the queue earlier. So in short, these behaviors, and you can see that larger vehicles will always create or slow down the discharge of the other flows behind them. So because of which, instead of a steady pattern, what we observe is a very fluctuating uh, discharge. So this is one of the problems that we are trying to address in this study. For instance, see, this is an example where you can see one of the cycle at an intersection, the discharge during one of the cycle at an intersection, and on the x-axis is the flow, and the y-axis is the green time. You can see when we overlap other cycles, you can see the changes, the difference in each of the cycle, how the flow is varying across each cycle. And then again, when we overlap a few more cycles, there is a complete disturbance in the pattern. Basically, it's not, you cannot identify a steady region of flow. And there is so the question that remains is, where do we draw the line? Where do we draw the steady line, and how long does that go? Whether it starts at this time interval or the first interval, or then it goes to the next one, or does it start from here, and how far does it go? Does it stop at 10 seconds or 15 seconds or 20 seconds? So that is the question that we are trying to address here. There are existing studies. So the basic existing literature in India is from the IRC model, which states that the saturation flow is a function of width, and this is the red line here shows what the value would be for this particular approach. So but there are various other factors which the study does not address, including what would be the same for a base intersection or a non-base intersection. What are the conditions that need to be taken? How much of the influence of other vehicle types are considered while describing the particular saturation flow? So these are some of the issues that we are trying to address with the study. So what does literature say about the existing studies? Broadly, we can see this in two ways. First part is the field measurement of saturation flow, which is wherein we are finding out what is the value of saturation flow from flow data that you can see on the field, or you can get from the field. So some examples would be the measurement using the highway capacity manual, where the inverse of saturation headway is considered. So basically, what the data from the field is taken in, and from that how the saturation flow is measured. That is one set of study. The next set would be saturation flow estimation models, where in the absence of a field data, how would we describe a saturation flow? How would we find out the saturation flow value? And another important component which springs out when we are going through literature is the passenger car unit estimation, where since this is specifically true for multi-class traffic streams, where we are dealing with different vehicle classes and what is their influence on estimating saturation flow. So the literature is studied in these three broad aspects. So coming to the field measurement of saturation flow. So we can broadly find three methods in literature which wherein the field saturation flow how saturation flow can be measured from the field. So there is the highway capacity manual method, which is the TRB's highway capacity manual And according to that, there is the second method is the Australian road research method, which is suggested by Akelic, and the third one is the Webster's method. Yes, so the assumption of each is shown. The assumption for the highway capacity manual is that the headway of vehicles that is discharging after the fourth vehicle in queue, the headway becomes stable and it's a constant value, and this constant headway is called the saturated headway, and the inverse of this headway will actually give us the what is the flow value, saturation flow value. And it is assume that the saturation, so how long does saturation last? It lasts till the end of the queue. So that is what is assumed in the highway capacity manual. In the Australian road research method suggests that we divide the entire flow region, which is the incremental graph, the steady part, and the down curve. So we can split the entire flow into three sections. So the first section is obviously the incremental part where we will not be able to identify the saturation flow, but the second section, which is the middle plateau region, is the saturated region, and the flow in that is the saturation flow, and however long the uh, interval lasts, it will be the saturation period. So, and the Webster's method is a little bit more, goes a little bit more into the microscopic part, as in it suggests that we divide the entire green period into multiple intervals, short intervals, such that each interval is the flow at the end of each interval is taken into account, and the consecutive intervals which have a steady flow will be considered saturated, and the interval in that the flow in those intervals will be taken as the saturation flow. So these are the three broad methods. Now, whether these methods are suitable for the non-lane based multi-class traffic streams, we will see. So the highway capacity manual, it just assumes that after the fourth vehicle, there is a steady headway. But this obviously is not true in our case because the queue discharge is not in an orderly fashion. And also we have a larger component of lateral headways coming into picture. So the highway capacity manual depends majorly on the longitudinal headway. And so it's suitable for lane-based traffic, but it might not be applicable for non-lane based traffic conditions. See, the ARR method would be suitable for lane-based as well as non-lane based, given that we are able to identify the saturated region. But that is also one major question that we have. And yeah, so what we come down to is the Webster's method, which considers multiple intervals during the flow, and will be since it's a microscopic, it will go much more into the details of the flow, and we will be able to capture the fluctuation properly, and perhaps from that we'll be able to get the saturation flow as well as the saturated region. So based on this, the literature, we can understand that the Webster's method is better suited for measuring the flow data for saturation flow. As far as saturation flow estimation models are concerned, which is in the absence of flow data or the kind of more into a planning perspective. So the general pattern is that there will be a base saturation flow model, and there will be adjustment factors. So the base saturation flow model is usually the saturation flow that is seen in a base signalized intersection or base approach, so how do we define a base approach? It's something mostly described as without any disturbances from maybe side friction due to parking, there is a proper pedestrian crosswalk, there is no bus stop. So there are these many factors which and there is the presence of all car condition and no other vehicle type So these and all are described as the base flow condition, and the adjustment factors will be each factor will be the adjustment to each of the factor which is deviating from the base condition. So base saturation flow for the highway capacity manual uses obviously the saturation headway, and it's a constant value for the so it's constant value, and for one lane it is described as 1900 vehicles, and whatever changes from the base, which is of course there's a description of base intersection in the highway capacity manual, and whatever is deviating from that is used in as a comes in as an adjustment factor. And there are other manuals like it's in the Indonesian highway capacity manual, which use width to measure the base to describe the base saturation flow. This is because and width is mainly used in non-lane based traffic conditions wherein vehicles can occupy any position on the road and there is no strict lane following behavior. So in such conditions, width is usually used to describe the base saturation flow, and whatever deviations as per the site condition is there from the base, adjustment factors will be used for each. Now, when we are talking about non-lane based multi-class traffic stream, it is very important to notice that passenger car units is a used like we need to convert the entire stream into a standardized unit, and obviously passenger car units come into picture here. So when it comes to PCU estimation for signalized intersection, you can see that there are multiple methods like the headway ratio method, there is the density ratio method, delay based method, and area occupancy method. So in each of this method, the conditions of a the conditions in a all car flow is compared with that of a flow with the study vehicle type. For instance, in the headway ratio method, the headway of a car and the headway of of the study vehicle is taken in as the ratio of the two is taken in as the PCU value. Similarly, density of a car versus the density of a subject vehicle. Delay based method, area occupancy method, which is a version of representing density in terms of non-lane based condition where the area occupied or the space occupied by a vehicle is considered as the predominant factor. So in each of this method, the underlying idea is that a measure of effectiveness is used as the it uses a basic measure of effective. For instance, headway is used because headway is in a way representing saturation flow or capacity of the approach. And similarly, it comes to density or delay based. So basically what the studies do is they consider a best measure of effectiveness at that point, and they use that to compare the flow in terms of an all-car stream and subject vehicles. So in this case, saturation flow, since saturation flow is used for estimation, is the primary measurement unit, and it is used for measuring capacity, is used in delay estimation as well as in signal timings. It forms the ideal candidate for PCU estimation. So in the study also proposes that we use saturation flow for PCU estimation. So so the takeaway that we get from literature is that first thing is that when it comes to measurement of saturation flow, Webster's method is found to be the most suitable. When it comes to estimation of PCU values, the saturation flow is the most ideal candidate. It is the basic fundamental unit which is used for measurements or describing other important factors at signalized intersection. And we also come to this understanding that for non-lane based traffic condition with a multi-class traffic conditions, a standard or a single flow measurement, saturation flow measurement method is not applicable. So the methods studies that are there are very much limited to whatever saturation flow can be measured from that particular area, subject to certain conditions. So we are looking into we want to look into a more generic form of saturation flow measurement, especially when it comes to multi-class traffic stream. So this basically forms the objective of the study. It aims at what we aim is to develop a model for estimation of saturation flow, such that we get the PCU values as well from the model, and the model. The thing is that we need the data from the saturated region for the development of this model. Now, the hypothesis based on which the study is built is that the discharge, which we have seen, it fluctuates during the saturation period. This fluctuation in discharge is due to the presence of a non-standard vehicle or a non-car vehicle that is present in the stream. So if it were an all-car vehicle, it will probably be a steady straight line. It won't have the fluctuations that we see in the data. So based on this hypothesis, the model yes, so the fundamentals of the model is developed based on this hypothesis. So suppose on the x-axis, if you see it's the number of vehicles, and the y-axis is the green time. We can see that the flow is fluctuating throughout the green time. So an expected saturation flow shown in the red line would be such that the PCU values would be such that it brings the flow of vehicles towards this saturated flow line. So PCU should be able to describe the deviation of the flows from the main saturation or the expected saturation flow value. And this we can sum based on the equation that saturation flow will obviously be the sum product of PCUs as well as flow values in each of the interval. So our model starts here. And if we have a regression form of the equation, it would look like this, where S is equal to sigma over J, xj pj times plus epsilon, where epsilon will be the residual error term, and x is the flow values for the particular vehicle class J, and P is the PCU values of the vehicle class. So basically, the idea is to find out the PCU values which will best fit the flow values to describe a saturation flow. Now, rewriting this equation, if we have the error term on one side and the other terms to the other side of the equation, we will see that we can rearrange the equation as such. And if we square this summation of this equation over various intervals. So far we have been talking about the PCU values or single flow or cycle. Now what we see is we have multiple intervals over which we have the data. So basically the sum of all the intervals should also give the same saturation flow value. In that term, we are summing the epsilon and the RHS, the LHS, and squaring them for better accuracy, so that we basically end up with the sum of squared errors. And the idea here is to minimize the sum of squared errors with an optimization model, such that the function would be as shown here, as z is equal to summation of the difference, or this is the error term shown within the brackets, which is the difference in expected saturation flow and the sum product of flows and PCU values. So basically what the model does is, or what we expect from the model is here the saturation flow value is also unknown, because we are not, it is also something that we are looking for. So the saturation flow and PCU values will form the decision variable. And the idea here is to find a best fit of saturation flow and the PCU values so that the difference between the two terms is minimal, or the sum of squared errors is minimal. So the constraint, the two constraints on the decision variables would be uh, the main constraint is that of a car, that is the PCU value of a car will always remain 1 because that is the standard vehicle that we are taking into consideration since it's a passenger car unit. And obviously the non-negativity constraint for the PCU and saturation flow values. So here the only input that comes in is the flow value, which is the classified flow value for each vehicle type J, and within a saturated interval I. So it yes, so this is the basic model. It must be noted that the data should be from the saturated interval. So so now what we have with us is an optimization model, and we need to ascertain that the model that we are using, or it will definitely converge into a unique solution, because since it's an minimization function, there should be a minimum to actually get that. So how do we test that? So what we did was we tested it using the Hessian matrix of the model. So Hessian is a matrix of second derivatives, and going back to the 12th standard mathematics, if the determinant of Hessian is non-negative, it will yield a unique and optimal solution. So the idea is to find out the Hessian of the objective function and check whether it is a non-negative value and that it will yield a unique and optimal solution. So for that, we did an illustration on we considered a stream with 4 vehicle types, modes 1, 2, 3, 4. And the objective function in such a case would look as shown here. As you can see, there are 4 vehicle types, so there will be 4 xi's and xj, pj values. And I here stands for the interval, so there will be, of course, multiple intervals, but basically the xp terms would be 4 in number, and this would be what the objective function would look like. So the Hessian of the matrix is a second derivative of each of the objective function. So this 5 by 5 matrix is the Hessian of the matrix. Here, the second derivative with respect to each of the term, with respect to S, P1, P2, P3, and P4. So we have a 5 by 5 matrix since there are 5 unknowns. And the determinant of the Hessian for this particular condition, where we have 4 vehicle types, would be as such. Here you must note that the principal diagonal elements are all positive. But that does not necessarily imply that it will have a non-negative Hessian. So what needs to be done is, when we have a set of data, we'll need to go ahead and calculate the Hessian of each of them, and the data set it should have a non-negative Hessian. In that condition only, we'll be able to arrive at a unique optimal solution for the model. So we have a model, an optimization model. We have tested the convergence, or we have described rules to test the convergence of the model. So before applying the model into field data, we wanted to test it on a hypothetical data to ensure that the output that we obtain from the model is actually valid and correct. Even though it might be unique and optimal, we need to make sure that it is the same optimal that we are looking for. So for this purpose, what we did was we generated an artificial data set, and it was actually generated using some basic calculations For instance, we use the vehicle proportion here. So, for instance, you can see here, if you can describe saturation flow as summation of flow times the proportion, and the flow, which is the xij, is actually the flow in each interval I. The classified flow in each interval I for a vehicle j. So it can be rewritten as such, which is kj times ij, where kj is the uh, proportion of that particular vehicle in the cycle, and xi will be the total flow in that interval. So Kij, basically Xij is expanded into as can be rewritten as Kj and Xi, and Xi being common for each interval, it is can be rewritten as S by rewritten to find S by summation of Kj and Pj, such that sum of all Kj's are 1. Now the flow, so basically what we have here is what we're trying here is to find out the flow values for known values of saturation flow and PCU. So if we know, or if we know a particular saturation flow and a particular set of PCU values, how can we describe the flow? And this flow again is used to test the developed model, and we'll check whether the results obtained from the model are same as what we are expecting from the or what we had started with in the first place. So here the saturation flow for this test data set was assumed to be 30, and the PCU values of 4 vehicle classes were considered, which is 0.5, 0.75, 1 and 2. So and based on these values, the proportion, so the unknown factor here is the proportion. These proportions were randomly generated such that sum of all proportions were 1 for each interval, and using that each flow in each interval, or classified flow in each interval, was calculated. So for instance, this is the data set that we used. So we have 4 different modes and we have 4 different proportions here. And using each of these, so basically this is the kj value. And using each of the kj value, we will find out what is the xij values. So this particular data set, this from intervals 1 to 16 and modes 1 to 4, this discharge value will form the input into the proposed model, and the once the model is run, we should get the output of saturation flow and PCU values as to what we were expecting. So there were 16 rows of data, flow data, and it's assumed that this is in the saturated region. And so the n value becomes 16 in the model. And there were 4 vehicle classes which were considered. So the m value would be 4. And the determinant of Hessian, again, it is a first step in before we get started. So the determinant of Hessian was found to be this value is shown here, 5.83 times 10 raised to 6, and which is obviously greater than 0, which indicates that our model will, or the data set will definitely lead to an optimal solution. And the output obtained was 30.02, and each of the PCU values were very close to what we were expecting. And you can see here the first order optimality, the objective function, and the variation of saturation flow, and PCU, which is the decision variables. So the variation of each of them across different iterations. The first order optimality represents the closeness of the solution at that iteration to the expected optimal solution. So you can see here that as the iterations goes by, the first order optimality is nearing 0. Similarly, objective function, which is the the idea is to minimize the errors, so that is also close to 0. Saturation flow value fluctuates and comes down to whatever the value that we were expecting, which is 30. And similarly, the PCU values are also converging to the expected solution. So basically, with this test, we ascertain that the data that we get from our model is true and optimal and unique. So we can go ahead and test this on the real field data. So for the field data, we collected videographic data from 6 approaches in Mumbai, and the widths were ranging from 7 meters to 11.5 meters. And these were mostly base approaches because they meaning that they were free from disturbances from pedestrians. They were free from disturbances from bus stops, nearby bus stops in the vicinity, for any side friction due to parking. Um, so all these factors. So from there we collected 4 hours of data. So it was in some locations it was in the morning, in some locations it was in the evening, and in some locations it was both morning and evening. So there were 4 hours of data in each at each approach, and the data was extracted, the data during each cycle time, so that once the green starts, at every 5 seconds the flow value was measured, and it was noted down for each vehicle class. So here we have considered 4 vehicle classes, which is 2-wheelers, 3-wheelers, cars, and trucks. So trucks includes the wider range of buses, trucks, and commercial vehicles. And so each of so we considered, so at the end we have a classified flow data and in each 5-second interval for each cycle along all these intersections. So that was quite a data intensive. Coming to what the discharge profile would look like, we can see here that there is an initial peak. The first 5 interval, there is a peak in discharge, and this is possibly due to the infiltration of 2-wheelers and them accumulating in the front of the queue. And after that, there is a decrease, and this continues for some time till the whole queue dissipates. So we come back to our question. So how do we start, or where does the saturation flow starts? What is the value, and how long does the saturated region last? So here, the first interval is the initial surge. We can see a surge in the initial discharge, as opposed to a gradual increase, which is seen in idle conditions. Although there is a surge, this is not the steady flow that is present throughout the discharge, and hence this flow cannot be taken into account for estimation of saturation flow by definition itself. So we will not be including this part, and we'll be taking forward from the 10-second interval onwards, as or we'll assume the 10-second interval to be saturated and start from that point. Now, coming to the initial surge, we dived in a little deeper to find out what might be the cause, or ascertain what the idea that we had of 2-wheelers being the main vehicles that discharge during the first interval. So we can see from this average plot. So this is the flow average of each of the vehicle type during the discharge, and we can see a real high spike in 2-wheelers in the first interval, which then comes down and steadies down after the second interval. So the infiltration of 2-wheelers and their accumulation in the front is actually giving out this particular spike in the surge in the initial discharge. So although this value is not taken into consideration for saturation flow estimation, it is quite important to be incorporated into the capacity, or as an adjustment factor also, which is done in the Indo-HCM. So, as discussed, the saturation flow period needs to be ascertained. How long? Because the data that we need for our model is the data from the saturated region. So although we have eliminated the first interval, data from the first interval, so we'll start with the second interval, and we will start by assuming that the data in the flow in the second interval is indeed saturated. So from there, what is done is every interval is statistically compared with the 10-second interval, data from the 10-second interval, and however long the comparison, or however long the data is seen to be comparable, the saturated region is assumed to continue till that period. I can show that with an example. For example, here there's a first interval we are not considering. The second interval is assumed to be saturated. This is can also be seen in other literatures as well, where the ARR method and the Webster's method, they suggest an approximate 10 seconds after which the saturated region starts. So we are in line with the other studies. Now, which of these intervals is saturated and for how long it might go on. So we take each data from each interval and compare it using a t-test, in this case with an alpha of 0.95. And the hypothesis would be that the difference in means between the 10-second interval and that of the interval under consideration is 0. So when the test is a success, so we will consider that region to be saturated. So for instance, here 10-second interval, data from 10-second interval is compared with the data from 15-second interval, and if they are statistically similar, then we assume the 15th second interval to be saturated. Similarly for the 20th second, but if at one point so for instance here, if the 25th second is not found to be statistically similar, then we stop right there, and in this case the saturation period would be from 10 seconds to 20 seconds, which is a 10-second duration in whole. So the data from these intervals alone will be taken in for the study. Now the input into the optimization. So so far we have got the data from the saturated period, which will be the input into the optimization model. So we had the field data, we have every 5-second interval, and we got statistically estimated the saturated region. From there, we move on to the convergence test, where the determinant of the Hessian must be greater than 0. So for each of the data set, we will find out what the Hessian is and ensure that it's greater than 0, so that we can use it for further analysis. And with this input, the saturated flow data, we will run our model, the optimization model, and the output would be the saturation flow and PCU values. So the PCU values for our study from the various intersections or approaches that we studied is this is one of the results from there. So we can see the box plot. It shows the minimum and maximum value as well as the median values. Basically, it gives the whole picture of each of the PCU value for each of the vehicle class. So what we can see here is the PCU value of two-wheeler is less than that of three-wheeler, and which is again less than that of a car, and which is less than that of a truck. So we had not given this condition into our optimization model, but the results are showing as such, which indicates that the logical consistency that we expect, the logical arrangement of PC values that we expect from the data is actually reflected in our results, indicating that our results are quite consistent, and they are able to logically get the correct values for PCU. Now comparing a little bit more deeper into the values, you can see that here the two values of two-wheelers is say here it's 25% and 27%, and the values of PCU values are also similar. In certain other conditions, for instance here, although the values of proportion are similar for two-wheelers cars and a slight variation in three-wheelers, you can see the similar values in PCU as well, with slight variation. And the major drastic difference comes in with the proportion of trucks. There is only a very slight variation in the proportion, but the resulting PC values is quite high, which indicates that the influence of truck on the stream is very high, even though the proportion might be less. Here again, the proportion of two-wheelers is the same, but the PCU values here are different. This is due to the difference in proportion of other vehicle types, which is actually influencing the PCU value of two-wheeler as well. And here in this condition, where the proportion of PCUs or the proportion of all vehicle types is quite similar, we can see that. So what these findings indicate is that even though the proportion of a vehicle, the proportion of a vehicle not only influences its own PCU values, but it influences the PCU values of other vehicles also. So the PCU model is able to incorporate the influence of the vehicles surrounding it and get the PCU and get the results as an interaction of all these vehicle types. So in a sense, the model is able to capture these interactions effectively. And as expected, so here the plot shows the PCU values versus proportion for each of the vehicle type. There is no significant pattern that we see because, as I said earlier, it's not dependent on its own proportion. It depends on the proportion of other vehicle types as well. And as for saturation flow estimation, we have so in during the study, what we also did was we divided the intersections or the approaches data from the approaches into multiple sets, so that we have almost similar number of observations, which is easier to compare and better to compare. So in a sense, it is the same intersection. 1A indicates morning peak, morning traffic, and 1B is the evening traffic. So the saturation flow should be the same because the intersection is the same, all conditions are the same, and that can be seen in the results as well here. Similarly for other streams also, 2A, 2A1, 2A2, these are the approaches with morning traffic. 2B is the approaches with evening traffic for the same approach, I mean to say. So there again, you can see a consistency in the estimated saturation flow. Basically, it indicates that our model is able to consistently estimate the saturation flow. Now, based on the insights, what we understood was there is a slight influence of width on saturation flow. And we also, since it's not relevant to estimate saturation flow for every lane, we went because it's a non-lane based traffic condition. It was best to use the approach width for estimation of or for developing a saturation flow model or a base saturation flow model in this case. So the variation of saturation flow in every unit meter of the approach was seen, and we can see from here the unit saturation flow is the saturation flow per hour in every meter of the approach for each width. And you can see here that it decreases steadily as width increases. If we have a linear model for that, or if we are assuming it to have a linear model, the model would look something like this, where SU is the unit saturation flow is equal to AW plus B, where A and B are the coefficients and W is the width of the road. Now, what this idea signifies, this unit saturation flow shows is that we might have experienced it while we are driving also, that in approaches with smaller widths, we see that the vehicles are packed more densely than approaches with larger widths, or maybe larger number of larger widths. So the dense packing, or even during discharge, the aggressiveness is aggressive behavior of discharge is higher for widths with lower or approaches with lower widths than compared to higher widths. So that element of non-lane based traffic or the discharge is coming into picture using unit saturation flow. And thereby from unit saturation flow, we are arriving at the equation for saturation flow, which is saturation flow would be unit saturation flow times the width, and with A and B, the calibration constants and the data that we obtained from our results, we can develop a saturation flow model as such, shown here, which is a second degree model indicating that saturation flow has a non-linear relationship with width. Now coming to the inference from the study, so the hypothesis that we use that PCU can define the unevenness of flow is can be confirmed with this study, and the model that we left up based on this hypothesis yields consistent results across all locations, and we can see that it is efficiently able to capture the vehicular interaction. The PCU values that result from the model are seen to have a logistical consistency with the size of and maneuverability of the vehicles that we see on the road. And it is PCU values are seen to depend overall on the stream composition rather than the individual composition. And again, unit saturation flow value is able to describe the discharging behavior in non-lane based multi-class traffic streams. So the study provides a novel saturation flow estimation or measurement model using field data, and the model is generic in the sense that it can accommodate more vehicle types. Although we have studied only 4, we can have more vehicle types, so we can even reduce the number of vehicle types. Additionally, it can be used to measure saturation flow in different conditions. We have only studied base here, but it is suitable for flow measurement in every other condition, weather conditions. And yeah, so along with the model, along with the saturation flow, we also get the PCU values that influence the behavior at signalized intersection. Now the results are seen to be consistent and reliable, and they are tested using hypothetical data sets, and also the mathematical properties are also ascertained before we use into field data. So as for future scope of the study, we can conclusively say that the initial surge of vehicles in discharge needs extensive study, and their effect on maybe arrival rates, arrival patterns, all these factors can are a promising direction of research. So we have a publication from the study. This is the online link. I can provide if required. So I think we can open for discussion.
Thank you, Remya. It's the time for interaction.
Okay, in that slide number, I think it's around 31 or something. The PCU variation for different vehicles. It could be seen that like for two-wheelers and all, see, the PCU ranges from around 0.17. Maybe the variation is around almost twice. And for trucks also, it seems almost the variation is almost twice. Around, I think the minimum comes out from 1.15, maybe even up to say 2.6 something. But the variation as observed for the three-wheeler, I don't see the variation is like say around, it's not that double or something. It's unlike the
other. Hello? Hello? Hello, I'm sorry, I'm not able to hear anything after three-wheelers.
Praveen, sound is not coming from your side.
Praveen, I
Okay,
think
okay. Can you hear me now?
Yeah.
Okay, so I actually lost after three-wheelers. So you were saying that three-wheelers do not double the difference in the.
Yeah, I was just asking that thing, like the two-wheelers, the variation was almost twice, whereas in the case of trucks also the variation was almost twice, but that variation was not observed in that case of the three-wheeler. What could be that reason for that thing? Or is there any thing which is significant for that
particular vehicle type, you're saying?
Yeah.
Okay, so so how I would see is rather than the effect of the main reason that the variation of truck is too high is because we have considered multiple vehicle types. For instance, the LCV, buses, trucks, everything into one picture. So that is one of the reason why truck might be double. Although when you say double, the number is quite significant when it comes to the value in itself. So for two-wheelers again, the number is. I think the way we look at it should be a little different than the saying that it is double the particular number. It would be more to see that the variation between the flow or the numbers is quite small. I think I would look at it in that perspective, indicating that we have a better results from the PCU values or from the model.
Okay, okay, but even then, but the three-wheeler is the only thing which stands apart, right?
Yeah, you can say that. And actually, I have not. One more thing I must say that I'm not thought in that direction. So we were mainly looking for the influence of one vehicle over the other, and in itself, based on the mean and the standard deviation values, the value seems to be within the expected range or within the deviation. So, yeah.
Okay, okay. Just one more question. Like, in case of that unit saturation flow, the saturation flow was computed per width, right?
Per meter width.
Per
Yeah.
meter width. At any point of time, whether the time factor, like per second or something, was considered.
Sorry.
Because to take in the case of the aggressiveness, normally, like in case of higher width, per second rate will be much higher, right? When compared to the lower width roads. Because actually I could see that in the inference part, like aggressiveness, I think it was somewhere told like in case of lower width roads, the driver seemed to be more aggressive than the higher width road. So I was just skeptical, like if the,
Okay, okay, aggressive, in the sense that um, there will be more, the gaps might be lesser, they might be closer to, like they might drive very close to the vehicle ahead of them in case of smaller roads than in case of wider roads. So what we mean to say is reflecting the denseness or the um, how many vehicles are occupied in 1 meter width of a road during discharge is different for a lower width road than with a higher width road. So in roads with lower widths, there will be more vehicle tending to be accommodated in 1 meter than with roads with higher width, where a little bit lesser number of vehicles will be there in 1 meter unit of the road.
Yeah, that's obvious. Like, but what I was like looking was like if you take the time factor into consideration, like per second flow for each bit. Is there any chance that they might be similar? Like because if you take per second flow for that could be somewhere. No, I was just inquiring. Like,
Okay. So so if you want to really know So we can see here the values in PCU per 5 seconds. So, and if we compare that across different widths, and for each, excuse me, I'll move the. Okay, so this is PCU per 5 seconds for each width. So you can see here, again, there is definitely a difference in the PCU values. And if we go by per meter again, it will eventually even reduce.
Okay, fine. Thank you.
Ma'am, there's a question from Mithun. How are the
Okay.
estimated PCU values from this research different or similar to the outcomes of the similar Indian research in this area? Also, was the effect of initial surge of traffic from the approaches considered in this analysis?
Okay, so I'll get the first question first. Can you please repeat that?
It is there in the chat box.
Okay, okay.
You want us to again repeat?
No, it's okay. I'll take a look. Different or similar to the outcomes of similar research seen in India. So how is it? Yeah, so considering research in other areas, we can see that the PCU values are aligned with the logical consistency and what is expected from generally from or what is seen in other research, because we can see that the PCU values of two-wheeler ranges within the usual range of 0.2 to 0.4845, and the two-wheelers is 0.4 to again 0.67, and car is obviously 1, and that of trucks is also within the range. So what we observe is PCU values are consistent with the expected outcome, and they are also logically consistent, even though we had not explicitly input that as a constraint in the model. Now coming to the effect of initial surge, yes, initial surge is not used here because we are focusing on the analysis of saturation flow during saturated interval, and initial surge is not a part of saturated interval because it is a one-off condition, and it is not considered for saturation, not considered as a part of saturated interval. Saturated region, by definition, is the prolonged existence of a high flow or the maximum flow. So since initial surge is only the initial part, it does not prolong uh, through the discharge. We cannot take it into estimation of saturation flow. But definitely initial surge will be a part of the capacity analysis, and it needs to be incorporated as a adjustment factor or so, wherein the additional vehicles that usually there is no initial surge expected in ideal traffic condition, but we have this in our condition, in our traffic condition, and this initial part is also using the same roads and is a part of the capacity, and that needs to be incorporated, and which you can see in the India highway capacity manual, where the initial surge is incorporated as an adjustment factor to the base saturation flow. Yeah, so that way it is taken into the modeling of capacity, but considering the estimation of saturation flow, the initial surge is not to be considered.
So, hi, this is Vasudevan.
Hi.
I have a small doubt. Yeah, similar to this previous question only, whether this red time affects this maybe initial surge or this saturation flow. Because in case, if you take two cases where in junction where less than 60 seconds or something has the red time, and in other case, if it is more than 60, maybe up to 120 seconds or something, then the queue will be, I mean, queue length will be large. And this kind of creep, as you told, that will also coming to the front side, right? maybe by two-wheelers and all. So will that affect the maybe the initial surge, or will that affect the saturation flow? Even though you are taking after 5 seconds or something, the saturation flow will consider after 5 or 10 seconds. Will this be influenced in that saturation flow?
So in this condition, what I can suggest is that we will have to look into the data and we'll have to see whether the initial surge is indeed 5 seconds alone or might go beyond that. So if you're suggesting that if the red time is too much, we might have a larger initial surge, or we might have a prolonged initial surge. Is that what you're?
Yeah, right, exactly.
Yes. So yeah, so in that case, we will need to go into the data, and because this idea is a measurement of saturation flow from field data, it might change according to field data, and we will have to take a more detailed look into the data and see whether the initial surge is indeed stopping at 5 seconds and or going into 10 seconds or whatever. So
Okay,
that would be the investigator's call.
right. Thank you.
Shalini, you can ask that question if you want.
So,
Or
Thank you, ma'am, for your presentation. Am I audible?
thank you. Yes, yes, I can hear you. Thank you.
It was very informative. And I would like to ask you a doubt regarding how to pursue for a study for the Kerala kind of signalized intersections, where we do come across a lot of non-based interaction, non-based
Yes.
conditions,
Mm.
like pedestrian activity, parking activity. Also, most of the approaches will be at gradient, and there may be bus stops also within 75 meters of stop line. So if we go for analyzing the adjustment factor for these non-based conditions, actually, how would you advise, like, whether we should go for considering each of the factors separately, or whether it can have a cumulative effect on the saturation flow, or what would be the approach advisable for taking into consideration the kind of signalized intersection studies that we do experience in Kerala?
Okay, so so what I would suggest is so basically from what I have presented, we have one model for estimation of saturation flow from field data, or the measurement of flow from field data. So this particular model, as I said, is generic and it can be used for all field conditions, whether it is base or non-base. And yeah, and the second part was, of course, the saturation flow model, which is specifically true for some base conditions with certain conditions. So the thing is that if you have a non-base condition, you can still go ahead and use the first model, the optimization model, and you can get the saturation flow using the model, because whatever impacts or the influences that the surroundings have on the flow will be reflected in the within the saturation flow. The optimization model will be able to capture that. So the saturation flow that you get will be for a non-base intersection of whatever the condition there is, and you can compare that with a base if you have, and you can compare that with a base condition and see what is the influence of these non-base conditions on the on the over the base condition, and devise a separate factor would be good, because you'll be able to carry over to the next. But if the study insists that or if you see based on your judgment that it might be a combined effect, or if you're not able to separate that effect, then obviously a combined factor for the intersection might be advised. I hope I
Thank you, ma'am. Thank you, ma'am.
Hello, Remya, this is Anish here. I had a
Yes,
few
please.
doubts.
Yes.
The one thing is that if we consider more number of modes, then will there be a change in the PCU values that we estimate? Because in the N2HCM also they consider small cars and cars as separate, and
Yes.
also MATs. multi-axle trucks and such modes. So if we consider multiple modes, will there be a change in the PCU values? And if so, this would be a dynamic sort of PCU that is given as the estimated value. We'll not be getting a particular value. And also the variations can be in some way related to the proportion of these vehicles in the stream, because in IRC also they are given PC values for 5% of mode presence, share of modes. And if it is more than that, there is another set of PC values that are given. So is there any particular proportion that we can say that below this, the PC values will be this much, and above this, it would be something else? So some correlation with that also have you studied?
Yeah, so your first question on what would be the effect if we have multiple or much more vehicle types. So yes, the PCU values will change because our comparative factor will be different, and the number of vehicles that we are comparing with will be different. Basically, the stream composition itself. Although the same stream, but we will be looking at it from different angles. So there will be, you can expect variations in the PCU values as the number of vehicles increase or decrease. For instance, in this case, the truck variation in truck PC value is quite high, and that is one of the reasons that we think is because that we have included multiple, even the smaller light commercial vehicles as well as the larger loaded trucks into the same category. So if we tend to split that, yes, there will be a difference. So I hope that's the first question. And the second one, what is the influence on proportion? So yes, there will be influence on proportion, but what we can see is not just the proportion of that individual vehicle. There will be the influence of proportion from other vehicles as well. So as you can see from one of the plots where we have tried to find out if there is any relationship between proportion and the particular PCU. We can see that it does not show any significant relationship, but we can see from the values or so from the numbers that there is an influence of other vehicles that is coming into picture. So so yeah, conclusively, it would be, like you said, a more dynamic method for of PCU, where it will change according to whatever conditions or number of vehicle types that we might be prescribing according to the study. I hope that clarifies.
Yeah, thank you.
And ma'am, two-wheeler proportion is found to be a very a much influencing factor as far as the flow or the discharge rate is considered. So, and the surge also had been an effect of the two-wheeler proportion. So, with the two-wheeler proportion at different junctions, whether there is any variation in the saturation flow.
So, at different junctions with based on two-wheeler proportion, is there any variation in saturation flow? Am I correct?
Yeah, some locations the two-wheeler proportions may be higher than the ordinary case, or at some places it might be another value. So since two-wheeler is found to be an influencing factor in saturation flow or the discharge rate, does it have an impact on the saturation flow estimation than when compared with the other vehicles?
Okay, so we did not explicitly study on two-wheeler, but what we found from the analysis is that the influence of two-wheeler, uh, as well as you can see some variation, strong variation in truck proportions also, where a small slight changes in truck proportion results in a very large change in PCU values. So the effect of all these vehicles is all coming into picture when we are estimating the saturation flow itself using the model. So whether there is an explicit influence of two-wheelers, we can see that there is an explicit influence in the initial search, but that is not entirely taken into consideration for saturation flow estimation, because initial search is not part of the saturated region of flow. But otherwise, yeah, so otherwise the effect of a vehicle type is taken in into the model by itself. But explicitly, if there is any relationship between two-wheeler proportions and saturation flow, that I must say is not being looked at.
Thank you, ma'am.
The saturation flow estimation, the equation you have shown,
Yes.
it is largely varying from the 525W concept, no?
Yeah. Yes, it is. So you're talking about the equation or the
I'm
model?
talking about the equation which was shown towards the end of the presentation.
Yes, yes. So
minus 10 point something plus 600
yes,
W. Yes.
So it could be the IRC suggests this value for almost all approach intersections, and what we have seen here, or we have developed from the results that we obtained from our model, is that there is an effect of width that is coming into picture, or that we have not considered in in a linear model. So basically we are suggesting a second degree model, or a non-linear relationship between width and saturation flow for multi-class traffic streams.
Any other questions? Raji is also there, huh? Raji, okay?
Yes.
Yes.
Remya,
Hello, ma'am.
how are you?
I'm good. How are you? This was a surprise.
You are speaking from Singapore or from here?
I'm from Singapore.
Yeah. You are, first of all, my hearty congratulations for the nice
Thank you.
presentation. The interaction also followed.
Thank you.
Okay. Then you are working in the same field or little different one?
Actually, I'm working in traffic incident management now,
Yeah.
and it's with the computer science department.
Oh, very good.
So it's a collaborative project.
For how long?
So this is it was a 1-year term. Now I have completed about 6 months. So
Yes. Family is also there?
yes, ma'am. Yes, yes.
Okay, convey my regards.
Sure.
Okay. Wish you all the best there.
Thank
Okay.
you. Thank you.
Okay. Okay, thank. Very good.
Thank you.
Any other question? Yeah.
Sorry, I forgot to tell you. She was my student.
And then I know. Others may not know.
Okay.
Good.
Thank you so much, ma'am, for coming. It's really a good surprise for me.
Fully. Okay.
Thank
Very
you.
good.
Okay, probably we'll close it.
Thank you, ma'am. Now I invite Dr. Vasudevan N, Junior Scientist NATPAC, to deliver the vote of thanks.
Good afternoon, everyone. On behalf of NATPAC, I would like to extend my heartfelt gratitude to each one of you for joining us today for this first TransPedia Research Talk on the topic saturation flow estimation at signalized intersections with multi-class traffic streams. It has been an enlightening and interesting session shedding light on saturation flow estimation. First and foremost, I would like to express my sincere thanks to our esteemed speaker, Dr. Remya K Padinjarapat, whose expertise and knowledge have truly captivated our audience. Thank you, Dr. Remya, for delivering an engaging and informative presentation. We are grateful for the knowledge and insights you shared with us today. I would like to express my gratitude to all the attendees for your presence and active involvement. The questions and discussions that followed the talk actually showcased your interest in the subject matter, and I appreciate your engagement. Finally, I would like to thank our director, section heads, and the organizing team for their support that made a smooth execution of this program. In conclusion, I believe we have all gained some valuable insights from today's technical talk, deepening our understanding on saturation flow estimation at signalized intersections. Thank you once again to everyone involved, and we look forward to hosting more technical talk in this series and continuing this legacy. Thank you.
Also, you missed the Professor Tom.
Oh, yes, actually, we thank you, sir. Thank you, Professor Tom, and all those professors who have joined here for making this even more successful. Thank you so much, sir.
Thank you.
Yeah, and sir, yeah, I would like to thank for giving me this platform to talk about my research and for bringing everyone in. That was really, it was really good. So thank you so much. And I thank Professor Tom as well for being with me through the PhD and guiding me through my studies. So yes, it was a very good talk, a very good discussion that we had with the team. And I hope I continue to be a part of it.
Yeah, very good, very good. And for lesson, we thought lesson it can be only 45 minutes to 1 hour, 60 minutes. The inaugural the talk is very informative. We went almost for 1.5 hours, more than 1.5 hours. Good, Remya. Okay, happy Onam to you. I don't know.
Happy Onam. Thank you, thank you.
Whether you're coming down to Palakkad to enjoy.
No, I don't think I'll be coming for Onam, but hopefully for Christmas.
Yeah, okay, fine. So next time when you're coming, you visit NATPAC also.
Sure, sir, sure, I'll do that.
We have an office at Ernakulam as well as Kozhikode. Two offices are there.
Oh, okay. Okay. Yeah.
You're welcome.
Sure, sir.
Good.
Thank you so much.
Thank you.
Thank you, everyone. So we are winding up this session. Thank you all.
Thank you.